Welcome to the Explainer. Today, we're going to peel back the layers on one of the most transformative technologies out there, the large language model.
You know that feeling, right? You type a question into something like ChatGPT, and boom, you get this magical answer. But here's the thing, it's not magic. It's an incredible feat of engineering. And in this explainer, we're going to pull back that curtain and show you exactly how these things are built, step by step.
All right, so here's the game plan. We're going to start with just a giant pile of text from the internet, and then we'll walk through the entire process of how you turn that into a machine that can actually, think. Okay, let's dive right in. Every single large language model starts right here, with the raw material. I mean, think about it. If you want to build an AI that knows about the world, you first have to give it the world to read.
So the process kicks off with a massive snapshot of the internet. We're talking billions of pages. But as you know, the web is messy. It's full of junk. So all of that raw data gets pushed through this huge cleaning pipeline. It's designed to filter out spam and malware, strip away all the website code to get to the pure text. And this is super important. Meticulously scrub out any personal info like names, addresses, you name it.
And after all that cleaning, what you're left with is just this colossal data set of text. To give you some scale, for a modern model like Meta's Llama 3, we're talking about 15 times trillion tokens. And those tokens are the fundamental units the AI uses to actually understand our language.
So, what exactly is a token? Well, the best way to think about it is like an atom of text. See, the model doesn't see individual letters, and it doesn't even always see whole words. It sees these little pieces. A really common word like the, that might be one token. But a more complex word like ubiquitous actually gets broken down into smaller parts. And you gotta remember this, because it's absolutely fundamental to how the AI sees and processes our language.
Okay, so we've got our 15 trillion tokens of clean text. Now the real work begins. This is called pre-training, and it's the first truly massive-scale learning phase for the AI.
Right. The model itself is basically a huge neural network with billions, and I mean billions, of settings. We call them parameters. I love this analogy from AI researcher Andrej Karpathy, who says to think of them like knobs on a giant DJ set. Training is the process of meticulously tuning all those billions of knobs until the output from the model perfectly matches the patterns it saw in all that text.
And you know what's wild? For all this massive computation, the model's job is surprisingly simple. Its only goal is to predict the next word, or more accurately, the next token. It just reads a sequence of tokens and learns to guess the most likely one to come next. That's it. But by doing this over and over and over again, billions and trillions of times, it starts to build this incredibly complex internal map of language, and of the world that language describes. So the end result of this giant next token prediction game is what we call a base model. You can think of it as a super powerful autocomplete, kind of like an internet simulator. It knows a ton of stuff, for sure, but it has zero sense of being an assistant. If you ask it a question, it might just spit out 10 more questions, just like it saw in some random internet forum. It's not yet that helpful, polished tool that we all know.
So, how do we get from that raw internet simulator to the helpful conversational assistant we actually want to use? Well, that all happens in the next part, the post-training stage. This is where we literally teach it a personality. And this stage involves a really dramatic shift in the data we use. Those 15 trillion internet tokens, we just set them aside. They're replaced with a much, much smaller but absolutely priceless data set, maybe a few 100,000 examples of perfect, ideal conversations. All of a sudden, it's not about quantity anymore. It's all about quality. So where does this high-quality data come from? It's created by teams of human labelers. They get prompts, sample questions, and really detailed rulebooks on how an ideal AI assistant should behave. It should be helpful, truthful, and harmless. Then they write out the perfect response. The model then keeps on training, but instead of predicting the next word from the messy internet, it's learning to predict the next word from these perfect conversations. It's basically absorbing that assistant personality.
Okay, so imitation is a fantastic start. The model can now act like a helpful assistant, which is great. But to get it to truly reason,
to actually solve complex problems, we need one last, really powerful stage, and that's reinforcement learning.
This school analogy really nails it. Pre-training? That was like reading the entire library. The fine-tuning we just talked about? That's like copying the teacher's perfect answers from the board. But this final stage, reinforcement learning, this is different. This is like being handed a bunch of practice problems and the answer key, and then being forced to figure out for yourself how to get from the problem to the solution. And here is the key difference, right here. With fine-tuning, the model is just imitating one single, perfect answer written by a human. But with reinforcement learning, it's a whole different ballgame. The model generates maybe hundreds of its own potential solutions, and then a separate reward system tells it, hey, that path worked, or nope, that one didn't. It learns by exploring and getting feedback.
And through this massive process of trial and error, something pretty incredible starts to happen. The model begins discovering problem-solving strategies all on its own. It learns to show its work, to reevaluate its own steps, to backtrack when it makes a mistake. These are human-like reasoning skills that emerge not because we programmed them in, but because the model was rewarded for finding the right answer on its own.
All right, so now that we've walked through this entire incredible building process, from a pile of raw text all the way to a reasoning engine, we can start to understand why, even after all that, it's still not perfect.
So, the big question, after all that training, is this AI infallible? The answer is a definite resounding no. And honestly, its failures are just as fascinating as its successes. The best way to think of its capabilities is like a block of Swiss cheese. It can be absolutely brilliant, tackling PhD-level questions in one breath, and then completely faceplant on something that seems simple to us. Ask it to count the letter R in strawberry or solve a basic logic puzzle, and it might just fail spectacularly. And why? Well, remember, it sees tokens, not letters. And some of these simple tasks actually require more thinking time, more steps than it's used to taking. And that leads us to probably the most important takeaway of all. You have to treat this thing like an incredibly powerful but very fallible intern. Use it as a tool, for sure, lean on it for inspiration and to get you started, but you always have to check its work and ultimately own the final product yourself. But this final stage of learning, this reinforcement and self-discovery, it's not just about fixing flaws. It's about something much bigger. It opens up a really fascinating future, one that goes way beyond just imitating what humans already know. We've actually seen hints of this before. Back in 2016, in the game of Go, the AI AlphaGo, which also learned through reinforcement learning, made a play that became famous. It's called Move 37, and it was so creative, so completely alien to human strategy that the best players in the world were just stunned. They thought it was a mistake, but it turned out to be a stroke of pure genius, a strategy that no human had ever even thought of. And that just leaves us with this one profound question. AlphaGo discovered a superhuman move in the closed, predictable world of a board game. So what happens when we apply that exact same process, that same ability to learn and discover on its own, to the vast, messy, open-ended world of human knowledge? What will be the Move 37, in science, or in art, or in thought itself? What kind of new thinking might emerge that's completely alien to us, but utterly brilliant? That is the exciting frontier we are just now beginning to explore.